today let's do examples on the application of full state feedback, right? So do some problems. Okay, so if you recall in the previous class, we looked at full state feedback where we are essentially designing the controller such that the control input u of t is some k times xt, right, for a memo system, or k dot xt for a SISO system, right? So the task for us is to find this control vector or control matrix K, right, to satisfy stability of the closed loop system and its performance. So that's where we stopped. We looked at yesterday, and we essentially formed the closed loop state matrix by considering the closed loop dynamics. And we need to ensure that the eigenvalues of the closed loop state matrix are placed at the appropriate locations. Okay, so that's where we stop. So let's continue from there. So we were considering this example, a single input, single output, second order LTA system. The task is to design a full state feedback controller for this system, such that the closed loop eigenvalues of the state matrix are placed or the eigenvalues of the closed loop state matrix are placed at -1 plus or minus k. Okay, so that is the problem that has been given to us. Always, when we are working with state space based design, the first step is always to calculate the equilibrium state, okay, of the system that has been given to us, and then we comment on the stability of the system, what we have been given. Then we go to control limit. Okay, so let's go in a sequence. So as we already know, if you want to calculate the equilibrium state, we need to solve AX star equals 0. In this particular case, that will mean 2, 3, 0, 1 times x1 star x2 star is equal to 0 and 0, right? So that's what we have. Now the point is this essentially leads to x star being 0. How? Because we know that we can observe that the matrix A is invertible, and as we already know, when the matrix A is invertible, there is a unique solution for x star, and that's the 0 solution, right? So, but just once again, let me write the two equations very explicitly. If you multiply the first row of A with the column vector x1 star, x2 star, we get 2x1 star plus 3x2 star equals 0. And the second equation will give us x2 star is equal to 0. So this implies that x1 star is also equal to 0. So consequently, the equilibrium state is the origin. Okay? So this is something which we can clearly identify. All right. So once we identify the equilibrium state, we need to comment on the stability of the equilibrium state, right? How do we figure out the stability? We find the eigenvalues of the state matrix, right? So if we solve determinant of lambda I minus a equal to 0, what would we get? We would get determinant of lambda minus 2 minus 3 0 lambda minus 1 to be equal to 0. This will give us lambda minus 2 times lambda minus 1 is equal to 0. So this will immediately result in the fact that the eigenvalues are 1 and 2. Okay. So the eigenvalues of the state matrix in this case are 1 and 2. So immediately we can conclude that the equilibrium state is unstable, right? So that's something we can immediately figure out. So we want to essentially now design a full state feedback controller to ensure that we not only make the closed loop system to be stable, but also we want to place the closed loop eigenvalue, the eigenvalues of the closed loop state matrix. Okay? Those are what are called closed loop eigenvalues at -1 plus or minus. All right. So before we go to controller design, we need to check for the controllability matrix. Okay, C subscript C, which we know that is given by B and AB in this case. Okay, so please note, in general, it is B, AB, A squared B all the way till A n power minus 1 B. In this particular example, the value of n is 2, right? So consequently, we have only till B and A. Okay, and if we were to calculate A multiplied by B, what will we get? So let's say we calculate A multiplied by B. The matrix A is 2, 3, 0, 1, and the vector B has been given as 1 and 1, right? As we can observe the problem statement. So the vector B is 1 and 1. So AB is going to be 5 and 1. All right, so that's what we are going to have, right, as the vector AB. So B is going to be 1 and 1. AB is going to be 5 and 1. Immediately we can observe that the rank of this matrix is 2. Right? How did we get it? Because we can observe that the two columns are linearly independent of each other. Right? So I cannot write one column as a multiple of the other. Right? The same is the story with the two rows. And also we can double check by calculating the determinant. So the determinant is also non-zero. Right? So the rank of this controllability matrix is 2. So the given system is completely controllable. So what does this imply? This implies that, as we learned yesterday, if we have a SISO system that is completely controllable, if you have a SISO system which is completely controllable, the bottom line is that, like, if we are given a specific set of closed loop eigenvalues, all of us will get the same control gain vector k. All right, so that is the idea. All right, so now let us go and find this k. All right, so once again, we will follow the sequence of steps. We are given a system. First, we calculate the equilibrium state. Then we calculate the eigenvalues of the state matrix to figure out the stability of the equilibrium state. Then we go and look at the controllability matrix to figure out the comment on the controllability of the system, right? This is given. All right. So having ascertained all these things, now let's go to the closed loop statement, ACL, which we know is A plus B outer product K. All right. So now this is going to be A is going to be 2, 3, 1 plus B is 1 and 1, right? Outer product K1 and K2, right? So if we recall from yesterday's discussion, the outer product of B and K, the ijth element will be Bikj. So if we were to do this, what we will have is that, like, the first element will be B1K1, B1 is 1, and B2 is also 1. Okay, this is a unique example where both elements of the P vector are 1. Need not be the case all the time, right? So you will see that we will have K1, K2, and then K1, K2, as the outer product. Okay, Bikj, right? So that's how we will get it. Okay, so please remember this. Okay, so if you want to get the outer product of B and K, the ijth element will be Bikj. Okay, I going from 1 and 2, and J also going from 1 and 2 in this particular case. All right, so that's how we get, right? So of course, let me not write this. In general, it will be I going from 1 to n. Okay, J going from 1. Okay, so let me write it that way because that is a general formula. Okay, so Bi, the outer product of B and K will be a matrix of size n by n. Right. So now we substitute this into this equation of KCL. So what we have is 2, 3, 0, 1 plus K1, K2, K1, K2. Once we have this, we have 2 plus K1, 3 plus K2, K1, 1 plus K2. Okay, that's our closed loop statement. Okay, so this is easy. Now, what do we need to do? We need to essentially calculate the determinant of lambda I minus ACL, right? That's the closed loop characteristic polynomial. So, if we were to calculate this, so we will do some algebra. Please follow the steps along with me. So, we will have lambda minus 2 plus K1, then minus 3 plus K2, minus K1, lambda minus 1 plus K2. Okay, so that's what we have. So if we cross multiply lambda minus 2 plus K1 times lambda minus 1 plus K2 is minus K1 times 3 plus K2. Okay, so this is what we have. Okay, so very simple algebra. Okay, so please stop me whenever there are questions. All right. So this is what we have. So now what we do is that we expand. All right. So what will we get? We'll get lambda square. Then if we collect the coefficients of lambda, we will have lambda times minus 2 minus K1 and then minus 1 minus K2. Okay, so that's what we'll have for the coefficient of lambda. And if you look at the constant term, it will be 2 plus K1 times 1 plus K2, right? Minus 3K1 minus K1, K2, right? That's the final term, right? As far as this expansion is concerned. So let's simplify a little bit more. Lambda square plus lambda times minus 3 minus K1 minus K2, right? So this is what we will have, plus 2 plus K1 plus 2K2 plus K1 K2, and just expanding the product of 2 plus K1 and 1 plus K2 minus 3K1 minus K1 K2. So we can see that plus K1 K2 and minus K1 K2 cancel off. So consequently, finally, we will have the closed loop characteristic polynomial as lambda square plus lambda times minus 3 minus K1 minus K2 plus 2 minus 2K1 plus 2. Okay, so we can see that this is a second order polynomial, right? So that's what. Okay, so now I hope the steps still here are clear, right? So pretty straightforward. We are just expanding the closed loop, what to say, polynomial, and we are essentially getting the closed loop characteristic polynomial as a second order polynomial. Now the question that we need to ask is that, like, how do we calculate K1 and K2 such that the closed loop eigenvalue, the closed loop eigenvalues are at -1 lesser. Okay, so that's what we are. Right? How do we do this? Now, of course, one can say, hey, look, I will solve this second order polynomial for its two roots. I will get the two roots in terms of K1 and K2. I will equate the two roots to -1 plus j and -1 minus j, right? So one could do that, but that's going to become a very, very roundabout way of doing things. Like, let's discuss a simpler way. As we know, this closed loop characteristic polynomial should be lambda minus lambda 1 desired times lambda minus lambda 2 desired, right? So that's something which we know. So lambda 1 desired, let's say it's minus 1 plus j. Lambda 2 desired is minus 1 minus j, right? Because those are the two desired closed loop eigenvalues, right? Are they not? Now what we do is that like we substitute it. Okay, so we have lambda minus 1 minus j, then we have lambda, sorry, it should be, I'm sorry about this, this is minus 1 plus j, consequently this will be lambda plus 1 minus j, and then lambda plus 1 plus j, okay, so that's what we have, okay, as the two factors, okay. Now, once we have this, like what we need to do is that like we need to expand now, right? So if we expand it, this is like two factors with what to say, which have complex conjugate parts. Like lambda plus one is the real part, and j is the imaginary part, right? Plus or minus. So if we expand this, we are going to say you can do this as an exercise. Like if you expand it, we are going to get lambda squared plus 2 lambda plus 2, right? So this is the closed loop characteristic polynomial that comes about uh, from the desired eigenvalues. Now we just need to match, right? So if we look at the closed loop characteristic polynomial in terms of the parameters k1 and k2, the coefficient of lambda is minus 3 minus k1 minus k2. So that should be equal to plus 2. Then if we look at the constant term, which is 2 minus 2k1 plus 2k2, that should be equal to plus 2. Okay, so now I hope all of us get the idea, right? How we essentially simplify the calculation process, right, of k1 and k2. So what we do is that like we look at the two polynomials and we equate the coefficient of lambda and constant, because the coefficient of lambda squared is anyway 1, right? So equating coefficient of lambda and the constant term, what do we get? So equating the coefficient of lambda and the constant term, we get minus 3 minus k1 minus k2 to be equal to plus 2. Then 2 minus 2k1 plus 2k2 is equal to plus 2. Okay? Yeah. So these are the two equations. So once we have this, like we just need to solve for k1 and k2, right? So if you look at these two equations, okay, so we can observe that there are two equations and two unknowns. So we just need to solve for the two unknowns, right? So if we look at this, you know, we essentially solve for this, right? First, now how do we simplify? Okay, let's say we first multiply this equation by both sides by minus 1. Okay, so we will get 3 plus k1 plus k2 equals minus 2. Okay, and let's say we multiply this on both sides by 2. Okay, so we'll get 6 plus 2k1 plus 2k2 is equal to minus 4. Okay. The other equation, if we just transfer it here, it's going to be 2 minus 2k1 plus 2k. That's equal to plus 2. Now we just add these two equations, right? So if I add these two equations, what is going to happen? This is going to cancel. We are going to get 8, right? Plus 4k2 is equal to -2, right? So this will give us K2 to be equal to -10/4 is equal to -2.5. Okay. Similarly, this would imply that K1 is going to be now equal to, if you look at from this equation, let's say we take from this equation, it's going to be -2, -3, minus K2, this is going to be -5, minus of -2.5, we will get once again -2.5. So this is a very, what to say, unique problem where both K1 and K2 are equal, okay, and they come out to be -2.5. Okay, need not be the case all the time. It's just that in this particular problem, both K1 and K2 are the same, and they take the value of -2.5. Right. So what have we done? We have taken the system under study. Right. We have looked at the equilibrium state. We have looked at the stability of the equilibrium state. Then we checked its complete controllability. Then what we did was that, like, we essentially designed a closed-loop control system such that the eigenvalues are placed at -1 plus or minus j, and we got a unique value, right, for K1 and K2, right? So that is the full state feedback controller driven process. So ultimately, we need to find the value of K, right? The controller gain, right? So which will give us the closed-loop eigenvalues at the appropriate location, and that's what we have done, right? So that completes the problem. As an exercise, what I am going to ask you to do is the following, just so that we can practice. So now, please find K such that the closed loop eigenvalue, sorry, closed loop eigenvalues are placed at -2 plus or minus j. Okay. All right. So that is the that is an exercise I'm going to do. So the system is the same. All right. So what I want you to do is essentially find the vector k such that the closed loop eigenvalues are at -2 plus or. Okay. So in fact, sorry, due to the fact that, like, we are essentially calculating the value of k to place the closed loop eigenvalues at certain locations, and as we know, the eigenvalues of state matrix, there is a correspondence between the eigenvalues of the state matrix and the poles of the transfer function. So this problem is also what is called as a pole placement problem. Okay, so if you encounter the term pole placement problem, what is being referred to is the problem of full state feedback, wherein we calculate this gain, controller gain, to place the closed loop poles or closed loop eigenvalues at certain desired locations. All right, so that is the problem. Okay, so I hope this is clear. All right. So now, moving on to another example. Now, what I'm going to do is that, like, I'm going to demonstrate how the controller canonical form is useful. So I hope all of us recall the controller canonical form, wherein we wrote down the state space representation from the governing ordinary differential equation, right? So if I can go to that location where we wrote down the controller canonical form. So in fact, for a system of order 2, this is what we wrote, right? So if we have a second order system whose governing equation was y double dot t plus a1 y dot t plus a2 y of t equals b1 u dot t plus b2 u of t, right? So the state matrix became 0, 1 minus A2 minus A1. The input vector is 0, 1. Okay, the output vector became B2 and B1. Okay, so this is the controller canonical form, right? So now the point is, like if you want to sort of like evaluate the significance of this controller canonical form, okay, let us consider a second order system. Okay, I'm going to take a particular example. We'll start from the beginning, right? So we will write down the controller canonical form, and then we will do the control design to figure out what is the specific advantage that we get. Okay, so let us consider a second order system whose governing equation is the following. Okay, so y double dot t plus y dot of t minus 2yt is equal to u of t. Okay, so this is the governing ODE, right? So we can immediately see that n is equal to 2, right? So, and we can immediately observe that by now we can immediately calculate the plant transfer function as the ratio of y of s by u of s as 1 by s squared plus s. Okay, so this is the plant transfer function. So immediately, if we map it to what we learned, right, as far as the controller canonical form, we can immediately see that the coefficient A1 is 1. Okay, the coefficient A2 is minus 2. The coefficient of B is U is B2, which is 1. Okay, and we can immediately see that B1 is 0, right, because there is no U dot term, like in this controller, in this governing equation. Okay, so consequently, the controller canonical form can be written as so. What is the controller canonical form? The state equation will be x dot t. That will be equal to, as we learn, the first row will be 0, 1. The second row will be minus A2 minus A1. Minus A2 is minus of minus 2, it will be 2. Minus A1 is minus 1, it will be 1 times x1t 2t. Okay, plus the input vector will be 0, 1. So we have 0, 1 u of t. Now the output term y of t is going to be equal to b2 b1, right? Dotted with x, the state vector x. So b2 is 1, b1 is 0. So this will be the controller canonical form. Okay, so this will be a state space representation of the given system in the controller canonical. Right? So I hope this is clear to everyone. All right. Okay. So now we will follow a similar set of processes, right? So that is, we will first figure out the equilibrium state. We will figure out the stability of the equilibrium state. Then we will figure out whether the system is completely controlled, right? So let's do the same set of steps. So to figure out the equilibrium state, we solve Ax star to be equal to 0, which will once again give us 0, 1. 2 minus 1 times x1 star x2 star is equal to 0 and 0. Okay, so we can immediately observe that A is invertible, so the equilibrium state is going to be 0, but still, like let's once again multiply the first row and the column x1 star x2 star. We'll get x1 star equal 0 as the first equation. The second equation will be 2x1 star minus x2 star equal to 0. So both these equations will lead to the fact that the equilibrium state x star is the origin, right? Is 0 and is 0 and okay, so that's something which we can immediately figure out. Now the next step is to figure out the eigenvalues, right? So if you look at the eigenvalues of the state matrix, we need to calculate determinant of lambda I minus A equal to 0. We have determinant of lambda minus 1, minus 2, and lambda plus 1. Okay, equal to 0. So, am I correct in my calculation? Yeah, that's right. So, if we do this, if we calculate the determinant, we will get lambda times lambda plus 1 minus 2 equal to 0. We will get lambda squared plus lambda minus 2 equal to 0. This can be written as lambda plus 2 times lambda minus 1. Okay, equal to. So the eigenvalues of the A matrix are going to be minus 2 and plus 1. So this implies that the system is unstable, or the equilibrium state is unstable. Okay, because we see that one of the eigenvalues is in the right of plane, right, at plus 1. So the equilibrium state is unstable. Okay, so that's what. So now let's evaluate complete controllability. Okay, so once again we calculate the controllability matrix. It will be B and AB. Why? Because n is equal to 2. We stop at n minus 1. This is 1. So B is 0 and 1. We calculate AB. Okay, so if I calculate here, the matrix A is 0, 1, 2, and minus 1. Okay, so that vector B is 0 and 1. So what we are going to get are 1 and minus 1. Okay, so this is what we are going to have. So we will have 1 and minus 1 as a second column. Right, so this will be the controllability matrix. Immediately we can observe that its rank is 2. Right, once again, both columns are linearly independent, both rows are also linearly independent, and the determinant is not. Right, so this implies that the system is completely controlled. Okay, so there is the conclusion. Okay. So now we need to figure out, where we will what to say, place the close to eigenvalue. So find K such that lambda desired, right? So will be, or let me write it properly such that the closed loop eigenvalues are of course S dot T dot means such that. Okay, so find K such that the closed loop eigenvalues are let's say once again minus 1 plus 7. Okay, just keep things simple. Okay, so let's do this problem. Right, so once again, as we know, ACL, which is the closed loop state matrix, is going to be A plus B outer product K. Right, so A in this case is going to be 0, 1, 2, and minus 1. Right, B is going to be the vector 0, 1, and K is going to be the vector K1. So now, if we evaluate B outer product K, what will we have? Please recall, right? If we take the outer product of B and K, we will get a n by n matrix. The ijth element will be Bijk. But please note that B1 is 0. So what will happen is that B1 K1 will be 0. B1 K2 also will be 0. So the first row of that matrix, B outer product K, will be 0. The reason being the element B1 is 0, right? In the second row, we'll get B2K1 and B2K2, right? The value of B2 is 1, so we'll just get K1 and K2, right? I hope it is clear how we got this expression, right? So this will give us the closed loop, the closed loop state matrix to be equal to 0 and 1, 2 plus k1 minus 1 plus k2. Okay, so this is one. Alright, so this is the closed loop statement. So as we know, the next step is to calculate the closed loop characteristic polynomial determinant of lambda I minus ACL. So if we calculate this, what are we going to get? We will get determinant of lambda minus 1 minus of 2 plus k1, then lambda plus 1 minus k2. Okay, so this is what we will have. So if we evaluate this, we will have lambda plus lambda plus 1, sorry, lambda times lambda plus 1 minus k2 minus 2 plus k. Right? So I hope the algebra is clear. Once again, please stop me if there are any questions. So I'm doing every step. So expanding this, we will get lambda square plus 1 minus k2 times lambda minus 2 plus k. Okay, so you can see that below it will be expanded. So we follow a similar process where we want to equate it to lambda minus lambda 1 design times lambda minus lambda 2 design. Okay, lambda 1 design is minus 1 plus j, so we will have lambda plus 1 minus j. Lambda 2 design, let's say it's minus 1 minus j, so we have, right? We just did this for the other column. So if we expand it, we will get lambda square plus 2 lambda. Right? Now, if we compare both these equations, right? We first compare the coefficients of lambda, right? So comparing the coefficient of lambda and the constant term, the polynomial, because at the end of the day, these are the same closed loop characteristic polynomial for the same system, right? So that's why we are comparing. If we compare them, we will get 1 minus k2 is equal to 2 minus 2 plus k1 is equal to 2. Right? We get two equations. Okay. Now, what is unique about this? What is the advantage we have obtained? We can immediately observe that the calculation of K1 and K2 have become decoupled. Okay. That is, if you look at the first equation, we have only K2, so we can explicitly calculate K2, right? So in the second equation, we have only K1, right? So we can explicitly calculate K1 from the second equation. So the calculation of K1 and K2 has become decoupled, right? And that is a big advantage of the controller canonical form. So what do I mean by this? Suppose if we go up, right? So to the previous example that we did, right? So if you look at the previous example, by comparing the coefficient of lambda and the constant term, of course we got two equations, right? There are two unknowns, two equations. But then we saw that, like we could not immediately get an explicit solution for K1 and K2, right? So K1 and K2 were there in both the equations, right? So consequently, what happens is that we had to do some more algebra to get the solution, right, for K1 and K2, right? But however, when we deal with the controller canonical form, it becomes decoupled. So this is a big advantage, right? Particularly when we go for higher order systems, right? Imagine, let's say we are having a 10th order system, right? We'll have K1 through K2. Right? In the previous method, we'll have 10 equations, 10 unknowns, can be solved, but then that process is going to be very tedious, right? However, when we use the controller canonical form, we will get 10 equations, but each equation will have exactly one unknown, right? Which will be the ith value of k, right? Ith entry of the vector k, right? So this becomes very, very easy to do, right? Once we express the what to say, the governing equation in the controller canonical form. So I hope the advantage of controller canonical form becomes clear to us, right? So consequently, what we have is that, like, if we express the system equations in the controller canonical form, the calculation of the control gain becomes very straightforward, right? So we get a decoupled equation when we are equating coefficients of the closed loop characteristic polynomial. So from here, we can, from the first equation, we can immediately see that K2 is going to be equal to -1. From the second equation, we can immediately observe that, calculate that K1 is going to be equal to -2. So the control gain vector becomes -4 and -1, right? So I hope it is clear how this helps us, right? Because we could decouple the calculation of the elements of the control gain, right? So that is a very, very important result. Okay. So what I'm going to leave you with an exercise problem for today is to do another practice problem, right? I'm going to give you another system, okay, whose governing equation is y double dot t plus y dot t minus 2yt is equal to u dot plus 2ut. Okay, so you can immediately see that I have changed the governing equation, right? So now there's u dot term also, right? So what I wanted to do is essentially design a full state feedback controller, okay, to uh, place the closed loop eigenvalue at -1 plus 7. Okay, so that is the problem. And essentially going to give you as an exercise problem. Okay, so once again, express it in the controller canonical form, right? Find the equilibrium state, comment on the stability, check for complete controllability, then you find the gain vector k. All right, so that is the exercise. Of course, lambda 1 desired and lambda 2 desired remain the same. The system has changed, right? So you will see that you will get the new set of values for k1 and k2. All right, so please do this as an exercise. Right? Okay. So I will just stop with one question, okay, that we can ponder about and come back for tomorrow's class. That is the following. See, the full state feedback, right, essentially proposes a control equation which is like u of t equals k times x of t for Memo system, or uh, k dot x of t for a SISO system, right? So now, if you have to implement it in real life, right, we need knowledge of state vector x, right? So we need information about the state vector at each and every instant of time. Now the question arises, how do we get this, right? So because we let's say, like we have a nth order system, right, or a 10th order system, right? Then we need values of x1 through xn, right, in order to calculate the control input using the full state feedback control equation that we would have derived. So that is a challenging exercise. Because even if you look at, let us say, a simple, quarter car suspension model, right? So you will have four state variables: the displacement of the sprung mass and unsprung mass, and the speed of the sprung mass and unsprung mass. So if we were to implement a controller, I'm taking quarter car model as an example, if you want to implement a suspension controller using even the simple model, we would require knowledge of 4 variables at each and every instant of time. But we may not have sensors to measure all these 4 variables, correct? Then what do we do? So that is going to lead us to another structural property called observability, which we will learn in tomorrow's class. And that is connected to what is called as design of state estimator. That is something we will discuss in the next class. Fine. So I just wanted to motivate so that we start thinking about it. All right. So are there any questions about what we discussed today?
No,
So,
sir.
yeah. Okay. If not, I will stop recording. We will continue in the next session. Thank you.